PyPSA-Eur, Open-TYNDP, what are the differences? One of the strengths of open source energy systems modeling is the ability to use, improve, and build on top of existing modeling frameworks. But with so many models, workflows, and frameworks, it can be hard to see how they actually relate to each other. This video clarifies what algebraic modeling languages like NumPy and energy system modeling frameworks like PyPSA are, how workflows such as PyPSA-Eur and Open-TYNDP differ, and along the way cover some important context on open source and energy systems modeling. Firstly, it is important to understand what algebraic modeling languages, energy system modeling frameworks, models, and workflows are to get a clearer understanding of energy modeling. First, we have the algebraic modeling language. This lets you express mathematical problems in code that reads almost like the equations themselves. For example, a constraint like generation plus storage discharge must cover demand can be written nearly word for word. Behind the scenes, the modeling language translates this into the low-level form, rows of coefficients and variables, that an optimization solver actually needs. There are many algebraic modeling languages, some open source such as NumPy, Pyomo, and Jump, and others proprietary such as GAMS. But none of this is specific to energy modeling, which is why a framework built on top is useful and simplifies things. So, secondly, we have the energy system modeling framework. Before we explain what energy system modeling frameworks are, it's helpful to think about what a software framework is in general. Think of a software framework as a toolbox or a pre-built structure that developers can use to build larger applications without having to start from scratch, and this allows developers to focus on more specific developments. Energy system modeling frameworks are built on top of algebraic modeling languages to solve energy-specific problems. In principle, you could write every constraint directly in a language like NumPy yourself, but an energy modeling framework like PyPSA already defines the common building blocks for you, for example, how a power plant, a transmission line, or a storage unit behaves mathematically, so you don't have to derive and code them from scratch each time. It also gives you a consistent structure for how components are added and connected, and it's optimized for performance on the large, complex problems energy systems produce. In short, it gives you the tool you need to prepare an optimization problem, for example, finding the minimum total system cost given a set of constraints. To actually build a model of the specific question you want to answer, you then need to populate the framework's building blocks with data and connect them together, which is what a modeling workflow does. A modeling workflow is the process that connects raw data with results. It creates the model, runs it to produce results, and processes the results. So, PyPSA-Eur and Open-TYNDP are modeling workflows that create instantiated models, not to be confused with scenarios or runs, scenarios being a coherent set of assumptions applied to a model, and runs being single solves or executions of a model. And one can think of a model as a representation of the system and the method used to answer a specific problem. Now that we covered the core concepts behind modeling languages, frameworks, models, and workflows, let's delve into how PyPSA, the framework, and PyPSA-Eur or Open-TYNDP, the workflows, are linked. PyPSA, which stands for Python for Power System Analysis, is an open-source Python framework for optimizing and simulating modern power and energy systems developed and maintained by many contributors. One could think of this as the base framework on which the many other PyPSA workflows are based on. PyPSA-Eur, on the other hand, is an open modeling workflow based on the PyPSA framework of the European energy system at the transmission network level that covers the full ENTSO-E area. Essentially, one can think of PyPSA-Eur as a pipeline made specifically for modeling Europe and thus using European-specific datasets and configurations based on the PyPSA framework. So what's Open-TYNDP's link with PyPSA then? Similarly to how PyPSA-Eur is an open modeling workflow of Europe based on PyPSA, Open-TYNDP is an adaptation of PyPSA Europe focusing on the replication of ENTSO-E's 10-year network development plan, or TYNDP. So the Open-TYNDP was built on and benefits from the open source PyPSA-Eur modeling workflow and builds on it for its specific purposes, configurations, and data. An advantage of an open source model and workflow is that you can structure the code to be able to use any data based on needs, whether private or public data. The Open-TYNDP, for example, replaced most of the default open PyPSA-Eur data with the public TYNDP data in its workflow where possible. Another advantage is that you can still benefit from changes made to the base modeling workflow, such as PyPSA-Eur for Open-TYNDP. Depending on how your own modeling workflow was developed, it is possible to take and integrate those changes with your own, and thus still benefit from improvements and features while still developing your modeling workflow as you see fit. If a modeling workflow is built using PyPSA, does that mean it is open source? Well, not necessarily. The PyPSA framework, as well as PyPSA-Eur and Open-TYNDP, are open source as it follows the 4 core freedoms which you can learn about in this video about open modeling. But, for example, a modeling workflow could be built on an open source framework like PyPSA, but if the code, data processing, and constraints are kept private, it would not qualify as an open source modeling workflow and thus open energy modeling, nor would it be any more transparent than a fully closed approach. Using an open source tool as a foundation does not, by itself, make the resulting workflow open source or transparent. Overall, it's important to understand the distinctions between modeling languages, frameworks, models, and workflows to better comprehend energy system modeling. When we say open energy modeling, it means that the entire workflow, from raw inputs to insights, is open. Whilst PyPSA is an open source framework, and many open source modeling workflows have been developed from it, not all models made with PyPSA are necessarily open source, and not all necessarily use open data. However, open frameworks like PyPSA and open workflows like PyPSA-Eur and Open-TYNDP are crucial for open energy modeling and decision making, as future models can use them as a base for tackling different projects, problems, and research, and external stakeholders such as policymakers, civil society, and researchers can inspect, understand, and verify the assumptions behind energy models. If you want to understand the core concepts behind open energy modeling, check out our explainer video.